Hello everyone, my name is Deepak Singh. I am a third year PhD scholar working under the guidance of Professor Amit C. Bhosle. So today I am going to demonstrate the contact pressure measurement between interface of GDL and bipolar plate along with the assembly and working of this PEM electrolyzer. So let's start with the measurement of this contact pressure between the GDL and bipolar plate interface. So in order to measure the contact resistance, we are going to use this double seat type pre-scale Fuji film which changes color with respect to the applied pressure. So as you know, contact pressure plays very important role in minimizing the internal contact resistance. So let's see how to find it. So first of all, in order to measure the contact resistance, we need to deassemble this cell, and after that we need to put that pre-scale film at the interface of GDL and bipolar plate. So let's deassemble this first. So these are the components of this electrolyzer cell. So basically, first you need to take out all the components, and so this is basically anode bipolar plate. This one is your gasket, and after that we will put this NEA. After that I will put this gasket, and now as we need to measure the contact pressure between this bipolar plate and GDL, so we are now going to put this LLW type seat at the interface of this bipolar plate and GDL. So after putting this seat, pre-scale seat, we need to further assemble it. So now we are going to apply a predefined torque of 3 Newton meter in order to assemble it. Always try to clamp this electrolyzer cell in diagonal manner in order to distribute the pressure uniformly. So now it is completely assembled. So now in order to see the effect of this clamping pressure, we need to take out this Fuji film. So for that we need to further deassemble it and take out that pre-scale film. So after opening it, you just take out this pre-scale film, and this change in color signifies basically the distribution of pressure. So more uniform distribution of pressure signifies more uniform distribution of color. So for further analysis, now we need to scan it with the help of scanner in order to get the quantitative value of the pressure at the interfacial contact. So in this way we are going to measure this contact pressure between the bipolar plate and GDL. Okay, so now this is our scanner through which we are going to scan it for quantitative analysis. So in order to scan it, first we need to go on this software Okay, so now go to this software of Fujifilm. Okay, after that go to this file and click on calibration sheet scan. So now it is asking for calibration sheet information. So now we need to put this calibration sheet on this scanner, and after that you need to click on this click on OK. So once the authentication is done, click on OK. Now we will put our film on this scanner. And now we will go to new standard scale, and now it is asking for the information like dates and something, and it is also asking for pressure scale type. So I have already told you that it is a LLW type pressure film. So click on OK and click on scanning. So after selecting the area for which you want to analyze the pressure distribution, now go to this image, and after that click on complete editing and click on OK. So you can see the pressure distribution inside this Fujifilm all over the surface. So you can find that where the contact is happening between the GDL and that bipolar plate, it is typically in the range of 1 megapascal. So but you can also see that there is some non-uniformity of pressure. So basically contact pressure management is an iterative process. You need to apply clamping pressure, and after that you need to check for the distribution of pressure, and once you get the desired value, you need not to apply further pressure for uniformity. You can also go to the file and take out this data in CSV format, and it is asking for whether you want data for whole area or partial area. So I am clicking on whole area. From there you can also save this data for further analysis. So hello everyone, now I am going to demonstrate the assembly and working of this PEM electrolyzer cell. Okay, so basically it's a single cell of 6.25 centimeter square of area. So these are the components of this cell. This is basically your anode bipolar plate, you can say monopolar plate. This is your cathode bipolar plate. These are your nut and bolts, and these are your gaskets, and this is basically membrane electrode assembly. So now we are going to see how to assemble PEM electrolyzer cell. So before assembling, we need to clean it with the help of IPA. Now we will put one by one all the components of this electrolyzer cell. After putting all the components one by one, we are going to clamp it with the help of torque wrench by applying the optimum torque. So as it is an optimized cell, so we are going to clamp it with the help of torque wrench by setting 4 Newton meter of torque. a torque in diagonal fashion in order to uniformly distribute the pressure all over the surface. So now it is completely assembled. Now we are going to demonstrate working of it. So okay, now I am going to demonstrate the working of this PEM electrolyzer cell. Okay, so these are the setup required for running an PEM electrolyzer cell. It consists of an heater which is used for heating this reactant, which is water, which we are going to supply to this electrolyzer with the help of this peristaltic pump. Okay, and so this is connected with this container through this peristaltic pump, and through this is going to this electrolyzer, in which it will pass through this channels, and ultimately it will come out and dispose in the same container. Okay, and this one is your DC power source, which is used for supply of the electricity to this cell. So before the connection to the power source, we need to do some priming in order to remove the trapped gases inside this flow field. So after doing the priming, we will connect it with the help of this power supply, and we will run this electrolyzer cell. Okay, so now I am going to connect it with this power supply. So we will connect anode side with positive and cathode side with the negative terminals. Okay, and you know the mechanism. As you supply this electricity to the water, it will split into H plus ions and oxygen gas. So oxygen gas will come out through this outlet pipe, and it will dispose in the same container, and H plus ion will pass through the membrane and go towards the cathode, and it will reduce and transform into the hydrogen gas, which we will get at this container. So after setting the voltage, once you start this supply of electricity, so once you start supplying electricity to this cell, so you can clearly see that hydrogen bubble is coming out and oxygen gas is going through this to the same container. So this is basically the whole setup for running an electrolyzer cell.
Hello everyone, I'm Akshay Sharma. I'm 4th year PhD student working under the guidance of Professor Amit Bhosle. Today I'm demonstrating how to prepare the membrane electrode assembly, that is MEA, and its performance evaluation in a proton exchange membrane fuel cell, that is PEM fuel cell. So starting with the MEA. MEA is the heart of fuel cells. It consists of a proton exchange membrane sandwiched between the two electrodes, that is anode electrode and cathode electrode. So in MEA, proton exchange membrane is mainly used to transfer the proton from anode to the cathode, and at the anode electrode, the oxidation of hydrogen will occur and it produce proton and electron, and at the cathode electron, the reduction of oxygen will occur and form water. So starting with the preparation of MEA, first we have to start with the preparation of catalyst ink. So catalyst ink consists of a platinum carbon catalyst dispersed in the mixture of water and solvent with the addition of optimal quantity of NaFeO 9-nomer. So NaFeO 9-nomer here is used as a binder which is used to proton conduction of ions into the catalyst layer. So as we know that in a hydrogen fuel cell, oxidation of hydrogen is a fast reaction, whereas reduction of oxygen is a sluggish reaction. So we need a different loading, that is we need a high loading of catalyst at the cathode side, and we need a lower loading of catalyst at the anode side. So here we have a two different loading of the catalyst, that is anode catalyst loading, and we have a different loading of catalyst as a cathoding. So it consists of the catalyst link dispersed in the mixture of IPA and water with the optimum quantity of ionomer. So next step is we have to coat the catalyst link into the electrode, that is GDL. So first we start with the anode GDL and anode catalyst link. So we will coat the catalyst link into the anode GDL using brush coating technique. So here is the brush. After coating the catalyst link into the GDL, next step to dry out the electrode to evaporate the residue solvent. So after the coating of anode catalyst link, next step is the coating of the cathode catalyst link into the cathode GDL. So here we also follow the same procedure using brush coating to coat the cathode catalyst link into the cathode GDL. So this is our cathode catalyst link. So here we will also follow the same thing. Now we have to be dry our electrode so our residual solvent can be evaporated. So catalyst loading on the GDL can be calculated by measuring the weight of the GDL before coating and after coating. So after coating of the catalyst onto the GDL, so our next step is the hot press of the electrode with the proton exchange membrane to form a MEA, that is membrane electrode assembly. So here is our cathode GDL. So this is our Nafion 212. And this is our anode GDL. For the optimum condition of the pressure and temperature is used for a hot press of electrode with a proton exchange membrane. Optimum condition of temperature and pressure is used for a hot press of the electrode with a proton exchange membrane to form a compact MEA. So this is our prepared MEA that consists of a proton exchange membrane and two GDL, that is anode GDL and cathode GDL. So after preparation of MEA, our next step is to test its performance using proton exchange membrane fuel cell. So we will start with the assembly of proton exchange membrane fuel cell. For the assembly of a proton exchange fuel cell consists of a end plate followed by the current collector, then bipolar plate followed by the gaskets, then MEA. So our fuel cell consists of a two half cell. First is the anode half cell and second is the cathode half cell. So now we start with the assembly of fuel cell. So first we have assembled the end plate, then current collector followed by GDL followed by gasket, then our prepare MEA, and this is our anode half cell, then followed by gasket, cathode bipolar plate, cathode current collector, cathode and plate. So after assembly of the fuel cells, next step is to apply a optimum torque of 3 Newton meter to maintain a uniform interfacial contact between the all component of fuel cell. Now after full assembly, we have to place our fuel cell in actual test setup condition. So this is our fuel cell test station. So this is our hydrogen and oxygen flow gases. This is our flow meter to control the rate of hydrogen and oxygen. This is our humidification to humidify our reactant gases, and this is our temperature controller to give the temperature, and this is our fuel cell. In fuel cell we know that at anode we supply a hydrogen where hydrogen is oxidized, and at cathode we supply oxygen where oxygen is reduced, and this is our potential stat that control the voltage and measure the current. So for the performance evaluation of MEA in a PAM fuel cell, first we start with the measurement IV, that is a polarization curve. So here we can see that our open circuit potential of the PAM fuel cell is 0.9. So then we go with the performance testing using IV curve. So this is our IV curve. So in IV curve we can change the voltage, and by changing the voltage we can measure the current. So in IV curve we also tell about the activation losses, ohmic losses and mass concentration losses. So in addition to the IV curve, our next performance is the EIS, that is electrochemical impedance spectroscopy, that mainly tell about the internal resistance and charge transfer resistance exist into the fuel cells. So this is our EIS of the fuel cell setup, that mainly tell about the internal resistance and charge transfer resistance. So performance evaluation in the PAM fuel cell, we measure the open circuit voltage, current density, power density, total resistance occurring in a setup, and its stability. So this is the demonstration of preparation of MEA, then assembly of MEA into the PAM fuel cell, and then its performance testing in a PAM fuel cell setup assembly. Thank you.